start out with, are there any questions?
I'm having trouble figuring out the second part of 5 when it's switched open.
The second part of 5. Let's see, nope, not that one. Not 22. Apparently I don't have 23 with me. That's the loop the wire a few centimeters above, sketch the induced current in d versus time. All right, so we've got I think it's in the XY plane.
Yeah.
All right, so I have a loop of wire down here. And that's my attempt to draw it is basically in this flat plane. X officially is coming out, and this is sitting parallel to that, to the XY plane, or in the XY plane. And then above it, we have another wire above it, which mysteriously disappears. This is hooked up to a battery or some sort of power supply, and there's a switch in there. So let's get rid of some of that. Or all of that. I think that's the setup.
Yeah.
And then we can, so right now, there's no current flowing through it because it's not a circuit. You need a completion in order for a current to flow through it. And so as soon as I connect it, this is going to induce a current. Sorry, not induce a current. This will produce a current in this black wire, and that will create a magnetic field, which will then go throughout. So if the way I have this written here is that it would create a current that is flowing from an overhead point of view clockwise. So the magnetic field would be downwards. So I have a north pole down here and a south pole coming in this way. And so in essence, I'm creating a magnet that looks kind of like that. So therefore, I go from no magnetic flux through this green loop to having a magnetic flux. And so therefore, a current is induced in the green wire. Now, the way this is set up, because I am suddenly creating a magnetic flux, I'm going to induce a current that is going to try to minimize that. It always tries to minimize the change. So since I'm creating it, it's going to try to destroy it. So the green wire will induce a current which would be counterclockwise. So it's going to produce a current going this way to create its magnetic field in that direction. And then I think it stays there for a couple of seconds, and then we undo the switch.
Right.
At which point the magnetic, so once you connect it, it's going to create an induced current. Eventually this current is going to be at a steady state. The magnetic field is going to be at a steady state, and therefore there's no change in the flux anymore, so the induced current, nada.
Okay.
And then when you disconnect it, suddenly we get a collapsing of it, and nature goes, wait a second, we don't want a collapsing of the magnetic field or the magnetic flux, and so therefore it's going to induce a current that will which will be in the same direction in order to bolster it.
So initially, the current increases one direction, and then it starts going the other direction, and then it goes back to 0.
The current starts off in one direction, and then when this current stabilizes, that current drops off to 0.
Okay.
And then when you unconnect it, then the current flips in the other direction.
Okay.
Probably gave too much of the answer away there, but so it goes. All right, did that answer your question?
Yes, thank
Okay.
you.
And this was number 5, or Master Set 23,
So also on Master Set 23, number 6 is a series RLC circuit.
right?
So to find the current, I assume we use our Vmax equals current times impedance formula.
That would be the current coming out of the power supply.
Right. So it asks for like, what's the maximum current and what's like the minimum current?
Oh, okay. So maximum current is potentially the amplitude, or for what we're doing in our nice ideal cases, it's the amplitude. It's the maximum current. But I don't think I gave you that much information. If you're trying to find the maximum amount, you have the Ohm's law analogs. I know that V equals IR. That's across the resistor. For the power supply, it's equal to IZ. For a capacitor, it's IX sub C, and for an inductor, IX sub L. So, will these formulas tell us the maximum or the RMS value or the minimum? Well, it depends. If this is max, then that is max. If this is RMS, then that's RMS. If that's minimum, that's minimum. So I think you have enough information to know, I think you know the max, or you can figure out the max of this, and you can find, or actually, no, for current. I can't remember the specifics of it. Do I tell you what the RMS value of the voltage is? Okay, from that you can find the maximum voltage. Impedance, I think you,
We were taught to calculate that earlier.
okay, so
That would give us the max current.
if that's the maximum voltage, that would be the maximum current.
Right, so the minimum current, you just,
Alright, so I have a current that's floating back and forth like that. And so let's say that this is 3 amps. What would this one down here be?
-3.
So what do you consider the minimum?
Zero.
Okay? I accept, for this situation, I would accept 0 or -3. My original thinking was -3, and then somebody put down 0, and I thought, oh, yeah, that actually, very easy argument to say that 0 is the minimum. So I accept either.
I know for the maximum current, for maximum current, so part B and 6, I use the formula to find the maximum current. It was like the maximum voltage divided by the impedance. Would
Yes.
that be correct?
Yep. Because it's a series circuit, the current's the same across all the components. Because I think the last question was what was the voltage across each component?
Yeah.
Yeah. So once you know what the current is from this, you can just now plug that into here. And at this point, you know R, X sub C, and X sub L. And so just calculate what the voltages are. Other questions? All right. Questions about something other than the master set? As a reminder, next Tuesday, we're doing the multiple choice, which will take up part of the class, not the entire class, and then a week from today is our last face-to-face meeting. Until we run into each other in the street and I go, I don't recognize you because you don't have a mask on. So. Well, Ian I've seen without a mask, and I've seen Gina without a mask, I think that's about it.
Are we doing corrections on 1B?
Yeah, due by Friday of next week.
Okay.
Where do we stand with that last master set?
So the chapter 28 master set? Oh, that's right, I was gonna make a decision on that. I recommend that you do it. If I remember, I'll post the solutions, but we'll just say it's not due. It does not have to be handed in. But the material is still fair game. Unless somebody really wants to hand it in for a grade. Just trying to be flexible. All right. Let's talk about special relativity. What is special about special relativity? As opposed to general relativity. Special relativity, acceleration is 0. So when you get into accelerated, so general relativity will deal with the warping of space and time because of mass, and it deals with accelerated reference frames. This deals with what are known as inertial reference frames, which is just basically a point of view with a constant velocity. We derived the relationship that time changes depending upon how fast you're moving. Or time is not the same depending upon how fast you're moving. The whole idea behind it is the fact that if I have a car coming towards me at 9/10 the speed of light, so a car coming at me at 0.9 times the speed of light, and its lights are on, and I try to measure, and I'm standing right here, so I should word that, 0.9 times the speed of light relative to me. And I have a detector here measuring the speed of light. I'm gonna measure the exact same value as if somebody is standing in here and this light shines in both directions, and he has a detector, he's gonna measure the speed of light the exact same as I will. But the speed of light, it has nothing to do with how fast you are moving relative to anyone else. And we have this relationship that time is equal to this proper time over the square root of 1 minus v squared over c squared. So proper time is the time for someone basically at rest. So with a lot of relativity problems, we have a rocket. We'll just say 0.9. Oh, let's do some notation here, just so I don't have to write as much. V over C shows up enough in relativity that they gave it its own symbol, the letter beta. This is a beta. Okay? Lowercase beta. So this formula here could be written as T is equal to TP over the square root of 1 minus beta squared. And to save some little time, I could just say up here then that the speed is equal to I don't have to say the speed now, I can just say that beta is 0.9. And that's the equivalent of saying the V is equal to 0.9c. Now this 1 over, so this is just TP times 1 over the square root of 1 minus beta squared. And this shows up enough that it gave its own symbol. a lowercase gamma. Times TB. And this is known as the Lorentz factor. So we can set up a little chart, and there is a video on this also, but at least we can do one of these. So got your calculator, trying to pull one out. So if beta is 0.1, gamma is something that someone will drop share with me, and then we'll do 0.9. We'll just do those three. So this is this 1 over the square root of 1 minus beta squared. Go out a couple decimal places.
0.005.
That's just a straight mark right there. So what? So you got the same?
Yes, and
Okay.
then for 0.9, I got 2.294.
0.99, I got 7.0888.
All right. So you can see that as we get closer to the speed of light, gamma starts having a much more significant change. From a physics point of view, this is the point right here in which we really start taking into relativistic effects into account, for the most part. GPS satellites take it into account, as has been mentioned before. They also take general relativity into account. But in terms of, from a practical point of view, if you're given a physics problem, if it's going underneath 10% the speed of light, we generally ignore all of this. So on this rocket over here, if beta is 0.9, and let's say it is, we have travelers on here and they go away and they come back to Earth. They start at planet Earth. And the people on the rocket ship age 1 month. Meanwhile, the person has a twin left behind on Earth. They're the exact same age when he leaves. He ages a month. How much did the twin age? Well, what's the relationship between the two times?
The same?
No, they are not the same. The twins will not be the same age anymore. Well, let's do some plug and chug. All right, so from this point of view here, we're taking, this is the proper time right here, 1 month. So I know that T is equal to gamma times TP. Gamma, when beta is 0.9, gamma is 2.294. So 2.294 times my proper time of 1 month. So how much is the other time? So the twin who was left behind on Earth is a little over 1¼ months older than his or her twin, the one who was on the rocket. Biologically, they are more than a month apart in age. Questions to hear, because I'm going to make it seem more complicated in a moment.
Why is the twin on the rocket the proper time, even though he's the one who's not really at rest?
What do you mean he's not at rest?
Because he's going 9/10 of the speed of light.
Oh, actually, that's how fast he's going relative to the person on Earth.
Okay.
But the person on the rocket, how fast does the person on the rocket think he's going?
Oh, he's at rest.
Yeah. But that does bring in what I'm gonna talk about next, known as the twin paradox. Let's see. So beta and gamma, so that was 0.1, 1.005, 0.9, 2.294, and 0.99, 7.0888. Read my own handwriting. Do notice that beta is unitless because it's a speed divided by a speed. So beta is unitless unless you want to come up with something bizarre, like, I guess you could have meters per centimeter, in which case, yeah, don't do it. Since beta is unitless, 1 minus beta squared is unitless, and so this whole gamma is unitless also. So they're just numbers. All right, so tagging on to this twin idea, I have identical twins on Earth, and one then gets into a rocket, and one stays behind. So from Earth's point of view,